Welcome everybody to this lecture where I would like to talk about the Dybvig banking crisis model. Let's have a look at the assumptions of the model. There are many ex-ante identical households. There are three different time periods: period 0, period 1 and period 2. The households of type 1 want to consume in period 1 and the households of type 2 want to consume in period 2. What is happening in period 0? In period 0, the households are born and they are endowed with 1 unit of a good. The households do not know whether they are of type 1 or type 2. So the households initially do not know whether they are getting hungry in period 1 or whether they are getting hungry in period 2. But the households know that they will be type 1 with a probability pi1 and they will be type 2 with the probability 1 minus pi1. What's going on in period 1? In period 1, it is the case that the households receive a private signal whether they are of type 1 or type 2. This signal is private, and it implies that the bank cannot control the signal. What does that mean? First of all, it is a case that the households receive an information. But this information does not arrive at the private household in form of a letter, because when the household opens the letter and receives the information that this household is type 1 and is already hungry in period 1, the household could take this letter to the bank and show this letter to the bank. It is more that the signal arrives in a private form and the household is not able to prove to the bank that the household is of type 1 or type 2. It's more the case that this signal arrives at a kind of Snapchat signal. The private household gets the information, I'm of type 1 or type 2, but the household is not able to make a screenshot of this Snapchat signal and prove it to the bank that the household is of type 1 or type 2. The signal is private to the household and the bank cannot control the signal. Let's have some assumptions with respect to the banking sector. The banking sector provides services in the form of a deposit contract. So the households, they are transferring their consumption good in period 0 to the banking sector. And the banks, they invest in period 0 the amount I in a long run project and the part 1 minus I in the short run project. The bank provides the option to cancel the contract and withdraw the investment either in period 1 or in period 2. The banks have two investment opportunities. There is a liquid short-term investment alternative, and the bank can terminate this kind of project either in period 1 or in period 2, and it yields no return. So the bank is just taking some liquidity, is putting it in the basement, and is not investing this good at all. It's very liquid because the banker just have to go to the seller, get the good out of the seller, and then can give it back to the private household either in period 1 or in period 2. The second investment opportunity is an illiquid long-term investment alternative. The intention of this project is that this investment should be terminated in period 2, so the bank should wait 2 periods until period 2 until the project is mature. The return is R larger than 1. Since R is larger than 1, the banks or the households, they have some kind of opportunity costs in case that they would opt for the short-term alternative. The long-term alternative provides a positive return at the cost of being illiquid. Also, the long-term investment alternative can be terminated in period 1, but it is costly to do so. In case that the bank already terminates the long-term project in period 1 prematurely, this long-term project will only yield a liquidation value, and this liquidation value is smaller than 1. The optimal allocation from the perspective of the households should lead to a split in the short-term and long-term investment so that the expected utility is maximized. The value I, which is between 0 and 1, will be invested in the long-term project, and 1 minus I will be invested in the short-term project. The budget constraints are as follows. The reflux from the short-term investment, 1 minus I, has to be large enough to finance consumption in period 1. That will occur with probability pi1. So it is the case that with a probability pi1, we want to consume C1 in period 1, and the reflux from the short-term investment is 1 minus I, and this should be large enough to finance consumption in period 1. The reflux from the long-term investment, I, needs to be large enough to finance consumption in period 2, which will occur with a probability 1 minus pi1. So with the probability 1 minus pi1, we are hungry in period 2. We want to consume C2. And the reflux from the long-term investment project has to be large enough. The reflux is I times R, like the investment, which is going into the long-term project, times the interest rate R. The banking sector or the bank is coming up with an altruistic deposit contract. Altruistic deposit contract implies that the bank acts in the best interest of the household. The bank doesn't want to fool the private household. The banks are acting in the best interest of the private households. So there exists a combination C1 star, C2 star, which leads to an optimum. The banking sector offers an altruistic deposit contract so that the households can realize their utility maximum. But there is one problem in the setup of this Dybvig model. It might be the case that a banking crisis emerges, and since this bank run would occur in an efficient equilibrium, in one that should maximize welfare to the society and the private households, this kind of bank run is labeled inefficient bank run. Let's have a look at the expectations of the households. The expectations, they play a very important role in this model. A household who learns in period 1 that he is of type 2 has two options. Option number 1 is no withdrawal in period 1, and the household waits until period 2, receives the amount C2 star in period 2, and consumes C2 star in period 2. Option number 2 is withdrawal in period 1 already. The household is entitled to get C1 star in period 1. The good could be stored in the fridge of the private household until period 2, and the household could consume C1 star in period 2. The household can only queue up once, so the household can either receive C1 star in period 1 or C2 star in period 2. The bank cannot differentiate whether household is of type 1 or type 2 because the bank has no insight into the private signal. In case that the signal would be public and not private, it would be possible for the bank to differentiate between type 1 and type 2 households. The bank would only pay out to type 1 in period 1 because only those households are hungry in period 1 and they need the liquidity in period 1 to finance consumption. So in case that the signal would arrive in form of a letter, then the bank could ask the private household, hey, please show me your letter. And then the bank would not pay out to type 2 households in period 1 prematurely. Why should a household of type 2 opt for option number 2? And why should a type 2 household already queue up in period 1? There are two scenarios with respect to the expectations related to the stability of the banking sector. The first equilibrium is type 2 households believe in the stability of the banking sector and then they do not withdraw their deposits in period 1. Second equilibrium is type 2 households do not believe in the stability of the banking sector and withdraw their deposits already in period 1. Then a bank run might occur. So it is a case that the expectations of the households of type 2 determine the equilibrium. And these expectations of the households are self-fulfilling prophecies, which implies in case that the type 2 households believe that the banking system is stable, the banking system is stable. In case that the type 2 households believe that the banking sector is unstable, the banking sector is unstable. Why can a bank run occur? Households of type 2 withdraw their deposits. They withdraw their deposits already in period 1. But in period 1, the bank has only liquidity from the short-term investment, and hence this liquidity position is just large enough to provide the liquidity for type 1 households. The banking sector has invested in the long-term project and therefore the bank has not enough liquidity to also serve type 2 households. The proportion of type 1 households is equal to pi 1, so that the bank needs funds of the size pi 1 C1 to match the demand for liquidity from type 1 households. In case that in addition some type 2 investors withdraw deposits due to an expected instability of the banking sector, the bank will indeed run into a liquidity problem, and due to the liquidity problem, the bank will terminate long-term investments prematurely. Premature liquidation of the long-run project will incur some costs because the bank does not receive R larger than 1, but only L smaller than 1. So the banks do not receive the high return R larger than 1, but only the liquidation value which is smaller than 1. Even if the bank terminate all long-term investments, it might be the case that liquidity is insufficient to serve the need for the liquidity completely. The risk emerges for type 2 households that their liquidity needs will not be served completely in period 2. Rational acting households are aware of this risk, and all type 2 households suddenly have an incentive to withdraw their deposits already in period 1. Households only get their deposits back in case that they show up at the bank in an early stage of the bank run. The banking system slides into a vicious cycle of ex ante expected and ex post indeed emerging instability of the banking sector. Let's have a look at a numerical example. We assume that the economy in the Dybvig world is characterized by the following parameters. So beta, which is the discount factor in the utility function, is equal to 2/3 to the power of 0.5. It really makes sense to use this numerical value, as you'll see later on. R, which is the return, is equal to 3/2, 1.5, so larger than 1. The liquidation value is 0.6, smaller than 1. And the probability pi1 is equal to 0.5, so with a 50% probability the household is of type 1, and with the 50% probability the household is of type 2. The function for the expected utility is given by this utility function. With the probability pi1, we are of type 1, and we consume C1 in period 1. And here it is the case that we take the square root of the amount consumed in period 1, so that the marginal utility of consumption is positive but decreasing. In the second part, we have the discount factor for consuming in period 2. 1 minus pi1 is the probability of being type 2 household, and then the type 2 household will consume C2. Also here, the quantity C2 goes to the power of 0.5, so the marginal utility is positive but decreasing. Your task is to compute the optimal level of investment. We should compute C1 and C2 as well as the expected utility level in the optimum. And in the end, we will assume that the economy consists out of 100 households, so that our numerical example makes sense. We'll start with the utility function and the two budget constraints. These two budget constraints, they should secure that we have enough reflux from the short-term projects to finance the consumption needs of type 1 households, and that we have enough reflux from the long-term project to finance the consumption needs of type 2 households. In the next step, we will solve the two budget constraints for C1 and C2, and then we will insert the result in the consumption function. So when we solve the first budget constraint for C1, we get that C1 is equal to 1 minus I divided by pi1, and we insert this stuff in the consumption function, so that we get the first term of the utility function. We solve the second budget constraint for C2. So we put 1 minus pi1 on the other hand side of the equation. We get that C2 is equal to R times I divided by 1 minus pi1. And we are inserting this right part instead of C2. When you look at this utility function, then it is the case that when you look at this utility function, it is the case that this utility function only depends on known variables, like pi1 is known and beta is known, R is also known, and the only unknown variable is I. The variable I is under control of the bank. So the bank should find the optimal I, the optimal investment amount which is invested into the long-term project. Therefore, it becomes clear that the bank should differentiate the utility function with respect to I, set this expression equal to 0, so that in the end we can find the optimal I, which leads to a utility maximum. The utility function is given by this expression here, and the bank has to find the optimal I, the optimal investment into the long-term project. So we have to differentiate the utility function with respect to I. Like one problem is that the I occurs here, like in this bracket to the power of 0.5, and a second time here in the second part of the utility function. Let's differentiate with respect to this I here. We have to take the exponent, write the exponent in front of the expression, compute the inner derivative. The inner derivative, when we differentiate with respect to this I here, is minus 1 over pi 1. And then it is the case that we have to reduce the exponent by 1 unit so that the exponent will take the value of minus 0.5. So in the first position, there is a pi 1, which stems from the utility function. Then we have to take the exponent and multiply through by the exponent. Then you can find here the inner derivative, like minus 1 over pi 1. And then it is a case that here we have the brackets, the term in brackets, multiplied through, but we have reduced the exponent by 1, so the exponent is minus 0.5. When we differentiate with respect to the second part, with respect to this I here, the inner derivative is r over 1 minus pi 1. We also write the 0.5 in front of the expression, multiply through by the inner derivative, and reduce the exponent by 1 unit. So the exponent will also take the value of minus 0.5. Let's have a look. Beta 1 minus pi 1 stems from this part of the utility function. We multiply through by this exponent. Then it is a case that we have the inner derivative here, r over 1 minus pi 1. And we take the term in brackets and reduce the exponent by 1 unit. This is like the first derivative, and we set the first derivative equal to 0. Once more, it is important to recognize here that I, the investment into the long-term project, is under control of the bank. The bank wants to find out how much should I invest into the long-term project I, and how much should the bank invest into the short-term project. Let's try to solve this equation here, and of course we have to solve this relationship for the unknown variable I, because then we know, the bank knows how much should be invested into the long-term project. Let's solve this expression for I. In the first step, it makes sense to put this stuff here on the other hand side of the equation. There is one minus sign here. When we put it on the other hand side of the equation, it will pop up with a positive sign. So in the next equation here, like the minus sign is gone and the equal sign is in between these two expressions. Then it is the case that we have a pi 1 here and a pi 1 there. So these probabilities will cancel out. We also have a 1 minus pi 1 here and a 1 minus pi 1 here in the denominator. So these probabilities will also cancel out. There is a 0.5 here and a 0.5 there. It will also cancel out. On the left-hand side, it is the case that only this term will pop up in this equation. And on the right-hand side, it is the case that we have a beta, we have an r, beta and r, and the term in brackets to the power of minus 0.5. In the next step, it is the case that we take both hand sides to the power of minus 2. So we are getting rid of this brackets here because of the fact that here we have a minus 0.5. When we multiply through by the minus 2, then this minus 0.5 will be gone. But it's also the case that we should consider that we have on the right hand side the terms beta and r, and when we take these two terms to the power of minus 2, then these terms will pop up in the denominator of the fraction to the power of 2. In the next step, we can multiply through by this pi1 here, so that we have 1 minus I on the left-hand side, and this pi1 goes to this fraction here, and r and I stands in between. In the next step, we put this I on the right-hand side of the equation, so we are adding I. We get to this expression here, 1 is equal to this term plus the I. Then we have 1i here and 1i there. We can write the I out of brackets. Then we get on the left-hand side, we have a 1 here, 1, then the I out of brackets. We get for the first term r times pi1 divided by b squared, r squared, and then 1 minus pi1 in the denominator. And this I out of brackets leads to a 1. So we have the 1 here and this term. In the next step, we divide by this term in brackets, because then we have isolated I on one hand side of the equation. So we get the I on one hand side of the equation and then 1 divided by the term in this bracket here. Then it is a case that here an r pops up in the numerator and in the denominator, so 1r will cancel out. This I here is the optimal amount the bank should invest into the long-term project. In our numerical example, pi1 was equal to 1 minus pi1 because pi1 was equal to 50%. It will be the case that these probabilities will cancel out. Then we have beta is equal to 2 over 3 to the power of 0.5. And r is equal to 1.5. Let's plug in these numbers. So the pi 1 and 1 minus pi 1, they cancel out because of the fact that we said type 1 and type 2 households pop up with the same probability. So these probabilities cancel out. Then we are left with 1b squared times r here. And we have beta is equal to 2 over 3 to the power of 0.5. Here we have to square beta. So this term here represents beta squared. And this 3 over 2 represents the r. 2 over 3 to the power of 0.5 to the power of 2 is equal to 2 over 3. 2 over 3 times 3 over 2 is equal to 1. So this fraction here is equal to 1. So I is equal to 1 over 1 plus 1. I is equal to 1/2 or 0.5. So after very long calculations, we received the insight that the bank should split the investment in the following way, that 0.5 units should be invested into the long-term project, so that 0.5 units, they are still available in the short-term project. Let's take into the consideration that we assumed that the economy consists out of 100 households. Each household received one good in period 0, so there are 100 goods available. The bank should split the investment 50-50, so the bank should invest 50 goods at the interest rate of R, which is equal to 1.5, into the long-term project, and this will lead to 75 goods in period 2. On average, we will have 50 customers of type 2, which will show up at the bank in period 2, so that each type 2 household can consume C2 equal to 75 over 50, like 75 goods, 50 households, 1.5. 50 goods are invested into the non-interest-bearing asset. So on average, 50 type 1 households will show up in period 1. And as a consequence, the bank has in period 1, 50 goods and 50 households. So the bank can pay out C1 is equal to 1 good. So C1 is equal to 1 and C2 is equal to 1.5. So this relationship highlights that if type 2 households believe that the banking system is stable, there is no incentive for type 2 households to queue up already in period 1 because of the fact that C2 is larger than C1. In case that a type 2 household who believes that the banking system is stable already queues up in period 1, this household only receives C1 is equal to 1 good, and this will be stored in the cellar of the private house, and then the type 2 household can only consume C1 is equal to 1 in period 2. But when the type 2 household who believes that the system is stable queues up in period 2, then he will receive C2 is equal to 1.5. On this slide, we try to highlight that the banking system increases expected utility. In the first step, we compute the expected utility in case the private household does not use the banking sector and just puts the good under the pillow. In this case, the expected utility is equal to 0.9. In case that the private agent uses the banking sector, utility increases. This stems especially from the fact that the banking sector is using the long-term investment project, which yields a positive return. So the banking system increases the expected utility. Let's go back to our numerical example and check what happens if a bank run occurs. In case that a bank run occurs, we will assume that all households line up randomly in front of the bank and that the bank starts to pay out each household according to the first come, first serve principle, the amount agreed upon in the contract. The question is, how many households will lose their wealth completely? If a bank run occurs in period 1, all households that show up in period 1 are entitled to receive 1 good unit because C1 is equal to 1. The bank will liquidate the long-term investment project, and there is I is equal to 50 long-term investment projects at the liquidation value of 0.6, which will yield I times L is equal to 50 times 0.6, 30 goods. Hence, the bank can distribute 50 goods, the liquidity which was held in the liquid short-term asset, plus 30 goods which stem from the long-term investment which was prematurely liquidated at the liquidation value. The bank has overall 80 goods in period 1. This lasts only for 80 divided by 1. It only lasts for 80 customers. The liquidity the banking system is able to generate will only last for 80 customers, and 20 customers will lose their wealth completely. So, of course, now we are able to understand why it is the case that in the end some private persons, they are disappointed from the banking sector. They had a very bad position in this queue, and it might be the case that this person is losing the wealth completely. Let's conclude. The idea of the Dybvig model is that a bank run can occur due to self-fulfilling prophecy with respect to the potential instability of the banking sector, even in case that the banking sector is inherently stable. Like here, it is the case that the banking sector acts in the best interest of the private households, and the bank does not start to gamble. The bank acts in the best interest of the private household. But the stability of the banking sector depends on the expectations of the households with respect to the stability of the banking sector. In the Dybvig model, it helps to introduce an institution which guarantees the stability of the banking sector in times of a liquidity crisis. So in this model, the lender of the last resort function of a central bank helps, because when the lender of the last resort or the central bank promise to pay if a bank or the whole banking sector becomes illiquid, this will stabilize the expectations of the private households. But there are also some negative side effects of this lender of the last resort. In case that the central bank guarantees the deposits, the depositors, like the private households, have no incentive to monitor the banking sector. No monitoring occurs. And then it might be the case that the bank have an incentive to invest in riskier projects, which will lead to losses of the society. So the bank advertise that they will invest in secure projects, but after they have collected the liquidity from the private sector, they will start to gamble. The banks will invest in risky projects so that moral hazard occurs after the lender of the last resort function was introduced. This will be highlighted in the second model, in the Milgram-Roberts model, which deals with the banking crisis and moral hazard. But first, I think it's a good idea to make a break here. Thank you very much that you attended this lecture. Thank you. Have a nice day. Bye-bye.